So say this is the transfer function we're going to be using. You can see we have it in Laplace form, but we don't want it in Laplace form. We want it in time constant form. Why time constant form? Because using Bode plots, we want to draw magnitude plots. So in decibels here and angular frequency here. This one's logarithmic, the W scale. And phase plots. So we want it in this form, JW, time constant form. So how do we do this? Basically, wherever you see S in the transfer form, you're going to be rewriting it as J omega. That's the first step. So in the bracket you have J omega, and second step would be whatever value you have in the brackets that is not equal to +1, we're going to have to change it to make it equal to +1. So here, I'm going to have to divide by 5, the value of J omega you're dividing. Here it's already 1, but it's nice to have it also divided by 1, doesn't make a difference, because these will be useful when you find your frequencies, your corner frequencies. This will be useful later. So anyway, what are we going to be plotting? We're going to have to be plotting on our magnitude plot the constant gain, this J omega, which with an S, which is a 0, and these two poles. Okay, so we said the magnitude plot looks like this, where this is the angular frequency in logarithmic scale, and here in decibels is your magnitude, normal scale. Okay, so what are we going to plot first? Let's say K. If we're going to be plotting K, one thing we forgot. Here, since we're dividing by 1 and 5, 1 times 5 equals 5, so we're going to have to add the value of 5 outside the bracket. This is your value of K. So basically, 1/5 is your value of K. So plotting this, if you have K, not green, this, K as 1/5, K is your constant gain. So this is the formula you use for plotting values of gain. 20 log, in this case, 20 log K. So 20 log 1/5. Plug this in your calculator and you're going to get minus 13.97, approximately minus 14 decibels. So if you draw this one, minus 14 decibels, somewhere here, is it going to have a slope? No, because it's constant gain. Constant gain, just a constant line, no slope. But where we will be having slopes is where the S's come in. So poles, zeros, J omegas, whatever you want to call them. For a value of S, you'd have plus or minus 20 decibels as your slope. For S squared, plus or minus 40 decibels for quadratics, but that's not the case now. So we've done K. Next up, let's look at J omega, which is basically a 0. When you have a 0, so something on the numerator, an S, or a pole, so an S on the denominator, what these two would have in common is the fact that they cross through at 1 on the frequency scale. So they cross through at 1, any value of pole or 0 you have on there. What else do they have in common? A slope, like we said. If it's just a single S, so not a squared or something, you have a slope of plus or minus 20 degrees. How do you know if it's plus? How do you know if it's minus? Well, if it's a 0, so the S is on the numerator, the slope is going to be positive, so plus 20 decibels. if you have a 0, if you have a pole, so a value of s on the denominator, the slope would be minus 20 decibels, so negative. This is the case we're looking at. So both cross out 1. We're talking about poles and zeros, just the value of s, just the slope changes. So we said slope of 20 decibels. This means here you have minus 20 decibels. And since the scale is logarithmic, you can see how it would progress. From 1, next up on the scale would be 10 for a full cycle of gradient, if I can call it that, of 20 decibels. And next up here would be plus 20. So 0, minus 20, 0, plus 20. That's how it progresses. 1, 10, 100, and so on. Okay. What else is left? Just these two poles. So, both of these poles, because they're inside the brackets, it's just useful to know that they're going to be starting at 0 on our magnitude plot. Purple. Okay, so at 0, they start at 0. And what happens to them? We need to find corner frequencies, so values of W. In this case, our corner frequencies, we said, are going to be the values by which we are dividing J omega. So your corner frequencies are 1 and 5. Why do we need corner frequencies? Because these are going to tell you when you have a slope that's coming in on your plot. So from constant gain, once you hit a corner frequency, you're going to have a slope of 20 decibels in this case, because there's no quadratic, so it's not 40. Okay, but is the slope going to be positive 20 or negative 20 decibels once you hit the corner frequency? Once again, it's the same as previously. Since we are looking at the denominator, so these are poles, they're going to have minus 20 decibel gradient once you hit the corner frequency. So we said we're starting off with constant gain from 0 until we hit the corner frequencies. Our first corner frequency is at 1. You can see here. So since it's a pole, minus 20 decibel slope. So minus 20. So like here, you can see will be your next one. And it just continues down. Next up, we have another corner frequency at 5. So once again, continuing from this line of 0 all the way to 5, so like somewhere here, you have constant. And then once again, because it's a pole, minus 20 decibel slope once you hit the corner frequency. If it was a 0, like the bracket as a 0 on the numerator, plus 20. So when you can see that it's not the same gradient. Okay, there we go. So that's also 20 decibel slope, minus 20. So yeah, that's it.